What if you were abducted by aliens? Don't panic. Humanity has long since etched a map home onto a golden record and cast it into deep space. 3 dead stars serve as your navigational beacons. This isn't just science fiction, it is a genuine survival contingency plan from space agencies. Want to know how to use this cosmic GPS to locate Earth? Today, we are going to talk about this essential cosmic survival kit. It is practically etched into your DNA. Today, we are discussing a hardcore piece of space survival knowledge. If one day you truly face an interstellar trek, how would you find your way home? The answer lies within one of the most peculiar celestial objects in the universe. It is called a pulsar. Simply put, a pulsar is the corpse left behind after a massive star dies. It is a special type of celestial body known as a neutron star. The name might sound unremarkable, but its physical properties are unimaginably extreme. The first characteristic of a pulsar is its extreme density. Its mass is comparable to the Sun, yet its size is only that of a city. This means the matter within it is compressed to the limit. A single teaspoon of pulsar matter could weigh over 1 billion tons. Any object we are familiar with would be crushed by its immense gravity. Its second characteristic is its extreme speed. Many pulsars rotate frantically. The fastest ones can spin over 700 times per second. This speed is more than 10 times that of a standard car engine. Its third characteristic is its extreme regularity. The rotation period of a pulsar is incredibly stable, surpassing even the most precise atomic clocks on Earth. The deviation is so small that it might only lose a second every few 100 million years. It is precisely these 3 extreme traits that transform pulsars from mere astronomical wonders into the key to our navigation and positioning in the universe. So for such a peculiar celestial body, how exactly is it born? To understand the origin of pulsars, we must first witness one of the most magnificent death feasts in the universe, the supernova explosion. The fate of every star in the universe depends on its mass at birth. Small to medium mass stars like the Sun will eventually fade away gently, becoming white dwarfs. But for those giant stars with more than 8 times the Sun's mass, their end is far more tragic. Over the course of hundreds of millions of years, the nuclear fusion reactions inside these giants burn like a massive engine, generating energy to counteract their own powerful gravity. When the fuel in its core is finally exhausted, this eons-long battle against gravity is lost. The star's core will, under the influence of gravity, undergo a catastrophic collapse. The outer layers of matter fall inward at extreme speeds and are then violently rebounded outward, forming a world-shattering massive explosion. This is a supernova. In just a few weeks, the energy it releases is more than the total radiation of the Sun over 10 billion years. It will instantly illuminate the entire galaxy it resides in. This explosion ejects most of the star's matter into space, becoming the raw material for birthing new stars and life. And at the core of the explosion, that former stellar core is compressed to the limit into a high-density object. This is a neutron star. Its interior is composed almost entirely of neutrons. The life of a star ends here, but a brand new cosmic miracle is born from it. The birth process of a neutron star also grants it a key characteristic, which is its ultra-high-speed rotation. Behind this lies one of the most fundamental laws of physics, conservation of angular momentum. You can imagine a figure skater. When she spins with her arms outstretched, her speed is relatively slow, but when she pulls her arms in close to her body, her rotation speed increases instantly. This is because her mass distribution has become more concentrated. The collapse of a star follows the same principle. A massive star, with a diameter of millions of kilometers, has its core compressed to a diameter of about 20 kilometers under the force of gravity. This process, where the radius shrinks tens of thousands of times, causes its rotation speed to be drastically accelerated, eventually forming a supergyroscope, spinning hundreds of times per second. But high-speed rotation alone is not enough to make it a pulsar. The key lies in another one of its characteristics, which is that it possesses an extremely powerful magnetic field. The magnetic field strength of a neutron star can reach trillions of times that of Earth's magnetic field. This powerful magnetic field captures charged particles around the star and beams them out along the direction of the magnetic poles, at speeds approaching the speed of light, forming a powerful beam of electromagnetic radiation, much like the light beam from a searchlight. Now imagine, this rapidly spinning top is also a cosmic searchlight emitting intense beams of light. Here is the most crucial point. Its magnetic axis and its axis of rotation are usually not aligned. There is an angle between them. This creates a very interesting effect. As the neutron star rotates, the radiation beam it emits sweeps through space like the beam of a lighthouse. If Earth happens to be in the path of this sweeping beam, then our radio telescopes on Earth will periodically receive a pulsed signal. When the neutron star's radiation beam points toward us, we receive a strong signal. When it rotates away, the signal disappears. This repeats over and over with extreme regularity. This is the pulsar phenomenon we observe from Earth. So, a pulsar is not actually beating or flickering like a heart. It is rotating and radiating steadily. It is this lighthouse effect that makes us think it is flickering. This extremely stable periodic signal is the pulsar's unique fingerprint. Every pulsar has a unique period, and it is incredibly stable. It becomes our only basis for identifying different cosmic lighthouses in the vast universe. With these cosmic lighthouses, we have the foundation for a map to find our way home. Now let's return to that cold alien spacecraft. Suppose you find a device capable of receiving electromagnetic waves. Congratulations, you have the first tool for your journey home. Your task is to use this device to locate at least 3 known pulsars in the sky. This is like finding familiar constellations in the night sky, except you are looking for stars with specific pulses. First, you need to measure the period of the pulse signal you receive. For example, if you find a star that pulses every 0.7 seconds, and you check the pulsar database established by humanity, you discover it is the famous Crab pulsar. You have successfully identified your first cosmic landmark. Using the same method, you continue to find 2 other pulsars and confirm their identities. Now you have 3 reference points with known locations. The next step is the most critical: trilateration. This principle is very similar to our GPS system on Earth. GPS satellites broadcast their precise location and time. Once your phone receives signals from at least 3 satellites, it calculates the tiny differences in signal arrival times to determine your distance from each satellite, thereby pinpointing your 2-dimensional or 3-dimensional position on Earth. The principle of pulsar navigation is the same. Because the speed of light is constant, the signals you receive from 3 different pulsars will arrive at your spacecraft at times that differ from a hypothetical cosmic reference time. This time difference directly corresponds to the distance between you and that pulsar. By precisely measuring the sequence and time differences of these 3 signals, you can set up a system of equations to solve for your current 3-dimensional spatial coordinates. The whole process sounds complex, but its mathematical foundation is simple triangulation. With 3 pulsars of known coordinates and a sufficiently precise clock, in theory, you can determine your position anywhere in the galaxy. This system is so reliable that as early as the 1970s, humanity etched it onto a metal plate and launched it into deep space. The Pioneer 10 probe, launched in 1972, carried a gold-plated aluminum plaque. Beyond information about humanity and the solar system, its core feature was a star map composed of 14 pulsars. This map uses the Sun as the center, indicating the direction of these 14 pulsars relative to the Sun, as well as their respective precise pulse periods. It is like a letter sent into the universe, with our home address written on it. Any intelligent civilization capable of decoding this map could use these cosmic lighthouses to find the location of the solar system. This grand concept, over the past decade, has remained largely in the stage of theory and contingency planning. Any intelligent civilization capable of deciphering this map could use these cosmic beacons to locate the solar system. Yet for the past decade, this grand concept has remained merely a theoretical contingency plan. To truly achieve reliable pulsar navigation, we need a vast and precise pulsar database. We need to know the positions and periods of as many pulsars as possible. This is much like building a GPS system. You need to launch enough satellites into orbit to achieve global coverage. On a cosmic scale, our satellites are pulsars, and our mission is to discover them. This grand mission reached a historic breakthrough in the 21st century. The protagonist is a national treasure hidden in the mountains of Guizhou, China, the 500-meter Aperture Spherical Radio Telescope, or FAST, which people prefer to call the China Sky Eye. FAST is currently the world's largest and most sensitive single-dish radio telescope. Its massive receiving surface is equivalent to 30 standard football fields, allowing it to capture extremely faint electromagnetic signals from the depths of the universe. Listening to the ancient heartbeats of pulsars is one of its core missions. Since its completion and commissioning in 2016, FAST has achieved remarkable success in searching for pulsars. As of the end of 2024, it has discovered over 1,000 new pulsars. This number exceeds the total discovered by all other telescopes worldwide during the same period. These include many extremely faint, rapidly rotating millisecond pulsars, as well as unique pulsars in binary systems. Every new discovery adds a new key coordinate point to our future interstellar navigation map. The exceptional performance of FAST means that humanity is shifting from passively waiting for pulsar signals to actively and systematically mapping the universe. We are not just preparing a roadmap for potential extraterrestrial visitors, but also preparing for humanity's own future. As we venture further into deep space, we will no longer be able to rely entirely on Earth's guidance. Spacecraft must have autonomous navigation capabilities and a pulsar navigation system with its coverage across the entire galaxy, and its extreme stability is undoubtedly the ultimate solution. The significance of pulsars extends far beyond navigation and positioning. They are unique, naturally occurring, physics laboratories in the universe. In the extreme density and strong gravitational environment of a pulsar, matter exhibits states we have never seen before, providing an excellent window for studying nuclear physics and fundamental particles. More importantly, the unparalleled periodic stability of pulsars makes them perfect tools for testing. Einstein's general relativity. Scientists have precisely measured the existence of gravitational waves by monitoring pulsar binary systems over long periods, work that has also been awarded the Nobel Prize in Physics. And now, astronomers are using millisecond pulsars scattered throughout the galaxy to form a massive network called a pulsar timing array. This network acts like a sensitive web covering the entire galaxy. When low-frequency gravitational wave ripples, generated by cosmic events, pass through the galaxy, they cause tiny fluctuations in space-time. These fluctuations cause the pulsar signals we receive to exhibit extremely faint yet regular variations in timing. By analyzing these variations, we may be able to detect gravitational wave signals from the Big Bang era for the first time. That would be a revolutionary breakthrough that opens a brand new window for observing the universe. From an accidental discovery by a young graduate student to a cosmic map written for extraterrestrials, and then to beacons for future interstellar travel and giant webs for detecting space-time ripples, the story of pulsars perfectly showcases the charm of human scientific exploration. It began with simple curiosity, but may ultimately point the way forward for our entire civilization. Well, friends, human knowledge is an island surrounded by an ocean of the unknown. Every exploration is like lighting a torch in the darkness. If this light has ignited your curiosity, please add fuel to our torch by liking, subscribing, and sharing. Every interaction of yours gives us the courage to take another step into the unknown. We will see you in the next episode. All represent the courage with which we step further into the unknown. Thanks for watching. If you enjoyed this journey through science, don't forget to like, subscribe, and share this video. See you in the next exploration with Quantara Atlas.